Kia ora and welcome back. In this video we're going to continue our chat about homomorphisms. Last video we introduced what these things were and we started looking at some of the properties that hold with elements. Just a quick recap on a couple of key features. A homomorphism basically is a function that preserves a group operation. So phi of A is going to be phi of A, phi of B, no matter what. And associated with that we had this set called the kernel, and the kernel is the set of all things in our group that map to the identity in our other group that we're mapping to. Now, the property, what we did just in the previous video is we essentially took our group and we established that the kernel was a subgroup, so that's good. So if we take cosets of the kernel, so we can always break a group up into its cosets. So if I take the kernel of phi here, this one might be A times the kernel of phi. Now I should have drawn this a bit better so they're all kind of equal sizes, but close enough. Okay, minor improvement perhaps. This might be B kernel of phi. So whenever we've got a subgroup, we can always partition our group into equal sized pieces using it. That's our standard coset stuff. Now what we discovered is that when we map, so this is our group G, and we're mapping into another group G bar, which is different. And so our mapping phi goes across here. Now what we discovered in our previous one, when we were looking at element properties, we realized that every element from one coset always maps to a single element in our group G bar. So from this one, everything in here is going to map to this point here. Similarly, you kind of get the idea, but let's just for completeness fill in the rest of the picture. Everything in this one maps to this point over here, and everything in the kernel maps to the identity. This is going to be E. So we can see that with the homomorphism, there is this sort of structure that's preserved. Our partitioning of our group into cosets of the kernel corresponds to distinct elements of the group we're mapping into. The other thing that's worth just remembering is that when we map into G bar, our mapping is not necessarily onto, so there can be other elements in G bar that are not mapped to at all. Okay, so there's no reason why our homomorphism has to cover the whole of G bar, but each coset does just map to a single distinct element. So you can see that we get the same number of things mapping onto one element, and that happens for every coset of the kernel. So that's kind of our understanding of homomorphisms thus far. And we proved a number of properties of elements that are preserved of elements when we go through homomorphisms. In this video, we're going to focus on subgroups. What happens if you send a subgroup through a homomorphism? What kinds of things map to a subgroup? Do normal subgroups get preserved backwards and forwards? All that kind of thing. We're going to go through these kind of things today. So buckle up. So our theorem is going to be called Properties of Subgroups under Homomorphisms. And we're going to have a standard setup with phi being a homomorphism from G to G bar, and we're going to have H being a subgroup of our group G. Okay, so our first property is that if I take phi of big H, now that just means I'm going to take everything inside my subgroup, pass it through my homomorphism, and collect all the results together. And that set that I get is a subgroup of G bar. That's our property. Okay, so how are we going to prove that? Well, we can just use our standard subgroup test. So we'll establish that it's non-empty. So first we'll note that phi of E is equal to E bar, which is therefore a member of phi of H because E is in big H, and hence our set phi of H is non-empty. That gives us free license to use our subgroup tests, so we'll use the one-step subgroup test. So I need to choose two elements of phi of big H and show that the two elements A times B inverse are also a member of phi of big H. So to choose two elements, I'm going to let phi of H1, phi of H2 be members of phi of big H. Okay, everything in phi of big H can be written this way, so I'm just going to jump straight to that point. Then I'm going to look at this element here, phi of H1, phi of H2 inverse. Right, now as we discovered in our previous video, we can bring the inverse inside. So it's going to be phi of h1, phi of h2 inverse. And because phi is operation preserving, I can bring the composition inside as well. And because h1, h2 inverse is a member of H, overall this element is a member of phi of H. So, phi of H is a subgroup of G bar by the one-step test. That's cool. So the first thing that we'd hope to be true is that if we got a subgroup in G, pass it through our homomorphism and we get a subgroup in G bar, so nothing breaks there. So we're on the right track. Number two, if H is cyclic, then phi of H is cyclic. Okay, so how are we going to do that? Well, let's just start by specifying what we've got. So let H be generated by A. Every time we're given a cyclic group, we can always write it in this form. We can pick a generator, which we'll call A here, and we'll say H is just the cyclic group generated by A. Then, now to show that phi of H is cyclic, we need to choose a member of phi of H and show that it can be written as the power of some generator. So we'll say let phi of H be a member of phi of big H. So there's our arbitrary member. Now I want to show that phi of H is equal to some power of something. So what I do know is that big H itself is cyclic, so my little h must be a power of A. We know that little h, which is inside my group G, is equal to A to the k for some k. So we can replace that and see what happens. So phi of H is equal to phi of A to the k, which is equal to phi of A all to the power of k by our operation preserving property. This means that phi of A is a generator of phi of H. It doesn't mean that phi of H is the same size as H. That might be something for you to think about for a bit. But phi of A is certainly a generator, and therefore phi of H is cyclic. Why is it cyclic? Because any element in phi of big H, such as this one here, can be represented as an integer power of some element phi of A. Our next one I'm not going to prove because it's quite straightforward, so I'll leave that one as an exercise. If our subgroup H is abelian, then phi of H is guaranteed to be abelian as well. Doesn't mean that our group G is abelian, but if we take an abelian subgroup of it, then passing that subgroup through phi will give us an abelian subgroup of G bar, no matter whether G bar is abelian or not also. That's cool. So again, it's quite straightforward to prove, and I'll let you just do that one for yourselves. Right, so our next statement applies to normal subgroups, and it says that if H is a normal subgroup of G, then phi of H is a normal subgroup of phi of G. Now, not of G bar, of phi of G. Let's just quickly draw a little illustration to show what's going on here. So remember, we've got our group G. There's our group G bar somewhere over here. Let's make it a funny shape just to illustrate that it's quite different. And I've got my subgroup H here. It's a bit smaller. So if I take H and map it through phi, then I will get some other thing, phi of H here. Right? The thing to realize here is that if I take my group G and map it through phi, then I don't necessarily get the whole of G, as I mentioned at the start. I just get some subset of it. So this one here would be phi of G. And what our property says is that if H is a normal subgroup of G, then phi of h is a normal subgroup of phi of g. Not necessarily a normal subgroup of g bar itself. We can't know that, but we can say that it's a normal subgroup of phi of g. Just good to practice drawing these diagrams to make sure we're clear on what sets and groups we're actually going to be dealing with here. Okay, so let's have a go at proving this one. We know h is normal in G, so we're going to make use of that somehow. And we have to show that phi of h is normal in phi of G. Okay, so we're going to use the normal subgroup test, which means we need to choose an arbitrary element of the subgroup. So let phi of h be a member of phi of big H, and an arbitrary member of the group that we're trying to show it's normal inside. And phi of G be a member of phi of big G. Now, we want to show that phi of G, phi of H, phi of G inverse is a member of phi of H. That is our normal subgroup test. We don't know this yet. This is what we are trying to establish. Okay, so we know, again, most of these proofs are going to have the same kind of idea, that we can start here and we're going to aim to combine these all together so we can somehow make use of H being normal in G. So, as we've done in previous ones, because it's a homomorphism, it's operation preserving, the inverse can come inside phi of G inverse at the end there, and those can be combined together like so. And because capital H is a normal subgroup of G by the normal subgroup test, this element here has to be a member of H. And therefore, overall, this thing is a member of phi of H as required. Hence, phi of H is a normal subgroup of phi of G. That wasn't so bad. You can see why it was we had to use phi of G, not G bar, because the arbitrary element of the group, which was phi of G here and here, I had to be able to go backwards through my homomorphism to make use of the normality of H. If I'd taken some element of G bar that wasn't in here, this one doesn't go backwards through the homomorphism because nothing maps to it. And so this whole property would not make sense. That's why we have to consider phi of G instead of G bar. Okay, our next property is one about the mapping phi. If our kernel has n things in it, then phi becomes an n-to-1 mapping from G to phi of G. This is just what I illustrated at the very start. Every kernel, everything inside one coset of the kernel maps to a distinct element, and there are n things in each one of those, and that's kind of the whole thing put together. So every coset, we've sort of already established this, but it's kind of stating it nicely. Every coset gets mapped, I better say what the coset's of. Every coset of the kernel of phi gets mapped to a distinct element of phi of G, and there are n elements per coset. Remember, all cosets are the same size and they partition our group G, and therefore our mapping is n to 1, because each of those cosets, which has n things, gets mapped to one element in phi of G. And that's all there is to that one. Alright, so the next one says if the order of our subgroup is n, then we map our subgroup through. We don't necessarily get a subgroup of the same size, but we do get a subgroup whose order divides n. Okay, so we're going to get the size of our new subgroup by dividing the size of our old subgroup by some positive integer, which may be 1. Okay, so what we're going to do is we're going to do a little trick to tidy things up a little bit here. So we've got our situation, which is G, H here, which maps to, let's color it in again, G bar, and we'll have phi of H in here. Okay, and so this is our mapping phi. So what we're going to do is we're going to say, actually, we're going to slightly change this up a little bit. We're going to delete G. And we're going to delete G bar. And we're just going to consider phi restricted to the elements of H. And we've got to call that phi H. Still the same mapping, but we don't care what happens outside of H. So we can just put our goggles on and zoom in just on this thing and consider this as a mapping from this one, and it's going to be onto phi of H, which is a nice property that it has. Okay, and we'll see why that helps us in a second. So we'll say let phi H be phi, but restricted to the elements of H. Cool. Then, phi H is a homomorphism from H, and it is actually onto phi of H. Okay, it's still a homomorphism, but at this time it's onto, which is important. So suppose the order of the kernel of phi H, because it's a homomorphism, it will have a kernel. Suppose the order of the kernel is T, then by our previous property, phi H is a T to 1 mapping onto phi of H, which means T times the order of phi of H gives me the order of H, i.e. the order of phi of H divides the order of H. Okay, so it's a nice little trick that let us get this onto mapping, and so we could just use the T to 1 property and we'd be all good. So for our next property, this one says that if K bar is a subgroup of G bar, as well as being a very chewy, sticky sweet, then this mapping, which is called the pre-image of K bar, basically it's a set of all things in our group that map to K bar. That's a subgroup of G. So again, an illustration is probably helpful here. So we've got G bar on the right hand side, and we've got K bar being a subgroup of G bar over here. Alright, now what we are envisioning here is we've got our group G, and the set phi inverse of K bar is called the pre-image of K bar, and that is all the things in G that map onto this set here. So you imagine there's sort of phi going this way, and phi inverse, which is kind of a generalized thing, going the other direction. Okay, because our mapping is many to 1, phi inverse of K bar is likely to be bigger than K bar. Okay, so what we're saying here is that if K bar, this thing on the right, is a subgroup of G bar, then we should be able to prove that this set here, which is phi inverse of K bar, is a subgroup of G itself. Alright, so let's have a crack at that. So again, quite clearly, the identity is a member of the pre-image of K bar. I'm going to call it the pre-image each time I write it down, even though I'm writing down phi inverse. It's good to get used to the terminology. Pre-image kind of makes sense. It's the things that happen before the image is taken that give you the image. So it's like the pre-image. So the identity is clearly a member of this because it's going to map to the identity in K bar. So that's fine. Which means our pre-image is non-empty, which means we can use one of the subgroup tests. Which means we're going to take two things in the pre-image and show that K1, K2 inverse is going to be a member of it as well. So let K1 and K2 be members of the pre-image of K bar. Then we want to show that K1, K2 inverse is also a member of the pre-image. So we're going to show that, we're going to take phi of K1, K2 inverse and show that we get something in K bar. Well, that's going to be equal to phi of K1, phi of K2 inverse, because phi is operation preserving. We also know that inverses can be taken outside, so it'll be phi of K1, phi of K2 inverse, and these two things are both in K bar by definition. Because otherwise they wouldn't, K1 and K2 would not be in the pre-image. So that is therefore an element of K bar as required. So that means that the pre-image of K bar is a subgroup of G. Okay, so the first one says what happens if we take a subgroup backwards through a homomorphism, in the sense of taking a pre-image, and property 8 says the same thing applies to normal subgroups. If K bar happens to be normal in G bar, then the pre-image of K bar is normal in G. Now, we've already sort of done some proofs like this one, so I'm going to leave that one as an exercise. Or you can consult Galleon for the details. But it's no harder than anything else we've been doing here. So you just want to do the normal subgroup test inside G and push the operation through to the K bar side of it so you can make use of K bar being normal. Similar to our other normal subgroup property that we did earlier on in this video. Okay, we've got one more property to do, which is number 9. If our mapping is onto, and it also has a trivial kernel, okay, remember trivial just means a trivial subgroup is just a subgroup comprising just the identity, then phi is an isomorphism from G to G bar. Alright, so essentially this is giving a couple of conditions we need to add to make phi into an isomorphism rather than just a homomorphism. So remember, isomorphisms are homomorphisms that are one-to-one and onto also. Alright, so we've been given that it's onto, so the only thing missing is the one-to-one property. But if kernel is just the identity, by property 5, which is sadly off the screen, let's scroll up and see it, even though it's going to make this look like a dog's breakfast for a second. Property 5, there it goes. If the kernel is, the order of the kernel is n, then phi is an n to 1 mapping. Okay, so order of the kernel is n, phi is n to 1. So for us, order of the kernel is 1, therefore phi is 1 to 1. Because the order of the kernel of phi equals 1, then phi is 1 to 1. And because it's also onto, as specified, therefore phi is an isomorphism. Alright, one corollary to this theorem, and then we'll finish off the video with a nice example. Okay, so a nice corollary is that kernels are always normal. Why is that? Well, if we take property 8, for K bar is just the identity. Alright, so what this says, a K bar is a normal subgroup, so the trivial subgroup is definitely normal. We know that phi of the kernel is just the identity, right? The pre-image of the identity is the kernel, and E bar is normal, hence the kernel of phi is normal in G. Alright, so whenever we have a kernel of a homomorphism, it's automatically a normal subgroup, which is a nice property, no matter what. As a matter of fact, let us check the length of this video, and I think we've done enough for one section, so I'll put the example in as a short addendum video. So, take care for now, we'll catch you later.